Right, we are going to get started on chapter 26. This is covering pages 496 to 499. We are going to look a little bit more about electromagnetism and how it affects something that we see every day. So we're going to be talking about light. And you may think, what is the difference between light and electromagnetism? Well, before we start that, let's look at some properties of light. It is the first thing that God made. So in Genesis 1, 3, and 4, God said, let there be light, and there was light. God saw the light was good. He separated the light from the darkness. It was the first thing he made, and it's the only thing we can see. You think you can see your computer and your phone and your book and your friend and your puppy dog, but if there's no light, you can't see that. What we see is light bouncing off of objects, bouncing into our eye, and our brain interprets that signal as a thing that we think we see. But light is really all we see. So anytime you have light, that means that at the beginning of that light, there has to be particles that are vibrating. So the motion of the electrons is what creates the light. So light is actually an electromagnetic phenomenon, and while we think that light encompasses everything because everything that we see is because light is bouncing off of it, we think it is super, super important. What we don't understand, what we don't know, we don't realize is how much of the world is going on around us that's in the electromagnetic spectrum that our eyes can't see. It is invisible to us because God has decided that we didn't need to see it at all. So electromagnetic wave, like I said, it starts from a vibrating charge, and a vibrating charge has an electric field, and a vibrating charge has a magnetic field. So an electromagnetic wave is a magnetic field and an electric field that regenerate one another. So remember, in order for a magnetic field to be made, you have to make the electric field. And then in order for it to continue, that electric field needs to drop and the magnetic field needs to drop. So these, they regenerate one another. As one grows, the other grows, and as one collapses, the other collapses. They are moving outward from any vibrating charge, and they are always going to be running perpendicular to one another. So if you can picture two jump ropes in a line, one is waving up and down, and the other is waving side to side, perpendicular to each other. And they are perpendicular to each other and to the motion of the wave. So it's in 3 dimensions right there. So if you've got one moving up and down, one moving side to side, but the motion of the wave is toward the far wall, you have 3 different planes that they are working in. So this would be an example of it. So you've got your electric field going up and down, your magnetic field going side to side, and the motion of the wave, that fancy word is propagation. Propagation means which direction it's moving, is going to be moving in a completely different direction, the 3rd plane there. So in order for the electric fields and the magnetic fields to remain in perfect balance and to be continually regenerating one another, they must be moving at a very specific speed. And that speed is 300,000 kilometers per second. Now, as light is passing through things, like as it's passing through the air, it's passing through a liquid, or through glass, it will slow down. But if it's in a void, like in between molecules, in between air molecules, in between glass molecules, out in space, it is going at 300,000 kilometers per second. So if it were to slow down, the fields would eventually weaken, and then energy couldn't be transported from one place to another. And it is really good that light and electromagnetic waves can travel through space without needing something to propagate them, because they propagate themselves. Because without it, we wouldn't get energy or light from the sun. We need it to be able to do that. God put that in place specifically for our benefit. Now, if it were to go any faster, then the fields would eventually become stronger and stronger and stronger, and that would violate the law of conservation of energy. So they have to go 300,000 kilometers per second, because that's what the fields need in order to remain. So if they weaken, they die. If they speed up, they violate the law of conservation of energy. Now, there was a guy named Maxwell who discovered that light is part of the electromagnetic spectrum. It is a type of radiation that is coming from the sun for us, and or any vibrating charge, and that the range of light that we see is between 4.3 times 10 to the 14th, which is what we would see as the color red, as far up as 7 times 10 to the 14th. So red is going to be the lowest frequency that we can see. Violet is the highest frequency that we can see. There are tons of different frequencies of waves that are below the range that we can see and that are above the range that we can see. Just like with hearing, there are things below the range that we can hear. That doesn't mean that they're not making sound. It just means that our ears can't detect them. So at a range that's below, our eyes and our brain can't see them. And at a range above, our eyes and our brain can't see them. So I want you to keep in mind, and this is really kind of hard to understand, is that regardless of how frequent the waves are passing over, electromagnetic radiation, everything within the electromagnetic spectrum is going the same speed. So radio waves, which are a type of electromagnetic wave, and ultraviolet waves and X-rays are all traveling at the same speed as light travels, which is 300,000 kilometers per second. So electromagnetic waves are classified according to their frequency, which means you need to know what frequency is. So frequency is going to be the number of vibrations per unit of time, or basically how fast it vibrates. And that is related to its wavelength, which is its distance between identical parts of a wave. So if we have our wave here, we have two main parts of our wave. We have our crest, which is here up at the top, and you have your trough, which is at the bottom. Your wavelength is how far it is between crest to crest, or if we were to continue this, we could say from trough to trough is our wavelength. Things that have a low frequency, like radio waves, doesn't mean they travel slower, it just means they have a low frequency. So what that means with wavelengths is that if we were to draw a radio wave, they would be really far apart. Doesn't mean it's traveling slower, it's just got really far distance between its hills and valleys. Now, high frequency, like an ultraviolet ray, is going to look a little different. It's got a high frequency, which means that it has a short wavelength. So it might look more like this, right? So between each crest is a shorter amount of distance, so they happen more often. Now, visible light makes up less than 1/1,000,000 of 1% of the measured electromagnetic spectrum. So 1% of the electromagnetic spectrum would be tiny, but 1/1,000,000 of 1% is extraordinarily small. We like to think that we can see everything and we know everything, but there's an awful lot out there just with our eyes open and we're looking around that we can't see. It's all invisible to us. We know that we can't see atoms and they make everything up, so that we kind of accept that that is all part of it. Because we could kind of see atoms if you consider them as a whole, as an element, or as an object. But for light, the light that we can see that illuminates everything that we can see is still a teeny, teeny, tiny little portion of what's out there. So like I said, wavelength and frequency are related. Long wavelengths have a low frequency, and short wavelengths have a high frequency. They happen more often. So this would be an example of the electromagnetic spectrum. I'm sorry, it's really hard to read, but down here on the low end of the frequency and the long wavelengths, we have radio and television waves. Next up would be microwaves. Those are going to be long waves. And then infrared. In between infrared and ultraviolet, somewhere right about in here, are going to be what we can see. So infrared is just below the red wavelength, and ultraviolet is just above the violet wavelength. And then after that, you'll have X-rays and gamma rays. Now on the test, there will be a squiggly line like this that you'll have to be able to put these words in the correct order of where we can see them. And the visible spectrum is going to fit right in there, in between infrared and ultraviolet. Now ultraviolet rays, you should recognize those as being the ones that give you a sunburn and how they move about. So those are pretty dangerous to us. And then infrared, we often think of those as heat waves. So if you ever drive down the road in the summer and it's really, really hot and you kind of see those wavy lines coming up off the road, that kind of weird distortion, those are going to be your infrared waves. Click on the link, complete the quiz, and I will see you in class.